Hello everyone, I hope you're all keeping well. So this is the page I stopped last time. I hope this differential equation is clear for everyone, but feel free to ask me question during the lecture class or even in lab. So for conclusion of that part, I would just refer to some important definitions that we had. One of them was damping. So, what is damping and how that influences the acceleration? So, if you're looking at a mass that is oscillating, how that damping affects that and prevents that from moving. So, deferring to that, we looked at something called damping ratio, and we looked at the equation that defines that. We also looked at angular frequency. So all these definitions are in previous slides, but if there's something confusing about them, feel free to ask me questions. And then we reached the point that we defined differential equation for some typical examples and systems. Now, we are looking at this example. It's suspension of a car. Many times we kind of refer to this example for very practical and everyday item that we are dealing with it, and it has a spring as a damper that is taking the pressure off the car. And the mechanism is very interesting, and it can be simplified to this system that we have. So this is the actual model, and this will be the system model. So from here we can actually look at the components and look at the differential equation. If you're interested to learn more about this particular example, I took the picture from this link, so you can look at that later on. Now, it's very useful to look at differential equation when our system has some sort of rotating motion involved. So if I look at a very basic shaft that has torque, and it means that the only movement, I'm assuming the only movement is the angular movement. So I don't have left or right or up and down. I only have angular movement toward that angle theta. So the target is to move toward that angle. So any force that is stopping or making it difficult will be the opposite direction. Many times we refer to angles as clockwise or anti-clockwise. So that is also another way of looking at. Right now, according to this picture, it is moving clockwise, the theta. So if we want to model this system, we are looking at something like this diagram here. So the mass itself can be assumed to be object, any shape of object that is trying to rotate. And then the forces that are trying to stop or avoid this movement can be modeled by spring and also a dashpot. We looked at these forces previously, but we didn't have it involved in a differential equation. Now, here, if I replace the x with theta in differential equation, and also I replace the inertia here, so I will end up with this equation. And then if I divide both sides with k, I will have this equation, as you can see. It is very similar to the one that we had earlier. It is very similar to the one that we have here, as you can see. It is only different because we are replacing the parameters from linear or straightforward movement to rotating or angular movements. And then we know that I here is the inertia, and then we have the constant that is k, and then we have our zeta and omega n. And just a reminder, what were they? They were damping ratio and angular rotation. Now let's move on to this example. This example is from book. So we assume that we have a mass, and then it is connected to two springs, K1 and K2. And then the force is trying to move the mass towards F direction. Now, the question is saying, derive the differential equation describing the relationship between the input of the force F and the output of displacement X for this system. So this displacement will be in direction of F. So any force that is trying to make that movement difficult will be opposite side. So the net force will be the F, because the F will be the positive sign. So we are considering it with positive sign. And there are two forces that are negative. One of them comes from the spring K1 and another one comes from spring K2. And we know that the force caused by these springs are negative because they are trying to make it difficult or stop that movement. So they will have that negative sign in front of them. And we have X there because of the definitions that come from the displacement caused by springs. On the other hand, we know that the net force is the force that is causing the mass to accelerate. So that net force is also at the same time equal to m second derivative of x over t. So when we put this one here and this one here equal to each other, we end up with this equation, and this will be our differential equation. As you can see, because we have two springs, so we have K1 plus K2. This part is very important. Now, let's move to another example. So in this example, I have same two springs, but in this case, we have two mass, M1 and M2. And the way that we are connecting them together is in a way that they are orthogonal to the ground. We assume this is a scenario here. So in this case, if we have a small movement toward the force F, we will have three types of displacement, as you can see. One of them is displacement x1, x2, and x3. So we are going to look at the equations and mathematics that is happening here. Now, the answer would say that first step is to consider just the mass m1 and the forces acting on it as shown in the diagram. This will be the simplified diagram. So we are going to concentrate on m1. So we ignore what is happening elsewhere. So we are going to look at the forces that are pulling m1 to up, and then we are looking at the forces that are pulling mass m1 to down. Now, this direction will be the positive direction, and the other direction will be the negative direction. So that is important to keep in mind. Now, book says there are the forces exerted by two springs. The force exerted by the lower spring is a result of that spring being stretched. The amount that it is stretched is x1 minus x2. So the difference between the x1 and x2 would be the amount that is result of stretch of this spring here. So the force would be a multiplication of K1 in that amount. So we end up with K1 multiplied in x1 minus x2. Now, in the other hand, if we look at the upper spring, the force exerted by upper spring is due to it being stretched by x2 minus x3. So if we multiply K2 in that, we are going to have that force. So if we look at the net force here, we said that the force that is coming from toward F will have the positive sign, and the other one will have a negative sign. So if we want to look at the net force, it would be this force, subtraction of this force and this force here. Now we are going to look at the net force in terms of accelerating M1. So if we have that and we put them equal to each other, so we are going to have this differential equation as a result of putting them equal to each other. Now we know that the force causing the extension of the lower spring is equal to K1 multiplying in x2 minus x1. So from here, we already know that this part has a name, and the name of that is called F. So if we take that in one side and we put the other one next to m, a second derivative of x, we will have this equation here, and then we can simplify it by replacing the k1 in x2 minus x1 with f. So this will be our final differential equation. Another example from book again, we have this object that is rotating, and we want to model it and write the differential equation. So as I explained, it can be modeled with a spring. This example is assumed to be a load that is rotating. So a motor is trying to rotate a load. That is the job of this system. So we can model it with the mass that is connected to a spring and a dashpot or damper, which are trying to make that rotation difficult or stop it. And so the model is explaining that the rotation torque will be on the positive side, and then ignore me with that arrow. I should remove that. That is here by mistake. We only have angular movement in this example. It's not clearly said that, but the motor is going to only rotate it. It's not moving it forward or backward or up and down. It's only angular movement involved. So in this case, when we have only rotation involved, we can refer to this differential equation. So we have t is equal to k theta plus c, derivative of theta over t, and inertia in second derivative of theta over time. So that would be the answer for this example. So the next section, we are going to look at electrical systems, and this will be the topic for next week. If you have any question from what I'm explaining in this recorded lecture, from the angular movement, from the examples that I explained, you can look at the reference book, the ebook, and you can also ask me questions during the lab or lecture. Okay, thank you.